previous discussion. Now, most of the problems that you will be able to read in John Copley's very short discussion, same thing with McCabe, is graphical in nature. So you will have to rely heavily on the graphical approach. So I intended to look for a different way of approaching leaching problems using empirical equations from other references. And one common reference that is most of the time a reference for the board examiners to get problems is Colson. And this is a problem, rather this is a formula that you can find only in Colson on the topic of leaching. So it allows you to determine the concentration of the solute in the solution at any time t. This C here, the concentration of the solute in the solution at any time t as a function of time, and you have here the other constants, but it's merely a function of time. So it has also the constant, which is the concentration of the saturated solution in contact with the particles. So concentration of the saturated solution in contact with the particles. So this is C sub S. Your K prime, which is a diffusion coefficient, your A, the area of the solid liquid interface, the B, which is the effective thickness of the liquid film surrounding the particles, are all, shall I say, empirically determined constants. Now, V is the total volume of the solution. And time, of course, is the time for the time in which you are supposed to determine the concentration of the solute in the bulk solution. Okay, so this is for leaching processes in which a pure solvent is being used. So your solvent is not supposed to have any solute present on it. And this can only be found in Colson. Now, as a sample problem for us to use this particular formula from Colson, so we have this. So this is single stage leaching, wherein you're going to use the time factor to determine the concentration. Now, in a pilot scale test using a vessel which is only 1 cubic meter in volume, a solute was leached from an inert solid, and the water was 75% saturated in 100 seconds. Now, if a full-scale unit, so weighing 500 kilograms of inert solid containing, just like before, 28% by mass of water-soluble component, so meaning the solute in this 500 kilogram of inert solid has 28% A. The same thing with that used in the pilot scale. If we use this 500 kilogram of inert solid, and it is agitated with 100 cubic meter of water, you are asked to determine how long will it take for the solute to dissolve, assuming conditions are equivalent to that in the pilot scale vessel. So how long will you need to dissolve or your solute in this 100 cubic meter of water if your solute is in a 500 kilogram inert solid matrix or in a mix together already, both weighing 500 kilograms. Now, water is said to be saturated with the solute at a concentration of 2.5 kilogram per cubic meter. So meaning if it is already saturated at that particular concentration, even if you're going to add more and more solid to be processed, it cannot anymore dissolve the given solid because it is already saturated. So let me just take a picture of this so we will not go back to the problem. Okay, now let's go to our solution. So there's a need for us to write down what we can work on in terms of the data in the pilot scale, and then use the same data or whatever relationship we can get there in the real thing, the one that is going to use the 500 kilogram matrix of solute and inert solid. So this is our first sample problem. So I will write here for the pilot testing. what are the information that we have. So the volume is 1 cubic meter. And then you have 75% saturated solid. So meaning the solid matrix that we are to process is 75% saturated. So the phrase is a solute was leached from an inner solid and water was used, was 75% saturated in 100 seconds. So the time it took for this 75% to be leached out is 100 seconds. So again, I will read the phrase. A solute was leached from an inert solid and the water was 75% saturated in 100 seconds. So it took 100 seconds for the water that was used in leaching out the solute to be 75% saturated. I think this is the only data that we have for the pilot testing. So for full scale, 500 kilogram of inert solid. So we have B. Now, you have to be very careful. It says here 500 kilogram of the inert solid containing, as before, 28% by mass of water-soluble component. So it could be easily confused that your 500 kilogram of inert solid is just B. But actually, this 500 kilogram of inert solid that is being referred to in here is the one that contains 28% by mass, your water-soluble component, since water was used in dissolving the solute. And that's your solute A in this case. So this 500, I will erase this, is not your just inert solid, but this is your solid containing the A already. Can't find my annotation. A class now. Let me share again. Where was I? So for your full scale operation, you have a 500 kilogram solid containing 28% soluble component. So that must be referring to A. So the phrase as before, so meaning as before, this one for the pilot testing, this also contains 28% A. So referring to the solid. So your solid that was used in the pilot testing also contained 28% by mass A. Excuse me, class. I will just have to close my Google because it seems like okay, so that's it. And then the volume of water that was used here is 100 cubic meter. The first one, we have a 1 cubic meter in volume a vessel. So it's not referring to the water, but the vessel that was used is just 1 cubic meter in volume. That is in the pilot testing. But in full scale operation, the 100 cubic meter here was really the water that was used in dissolving the solute. So this is really your solvent. So this is your solvent. I like to label this as 2 because that's how we label the solvent. This one is the volume of the equipment or of the vessel. Now, how long will it take for the solute to dissolve, assuming conditions are equivalent to that in the pilot scale vessel? So if this is your full scale operation, you are asked here for the time. So you are asked for that time in the full scale operation for to have the same recovery. So meaning 75% of your A in your solid must be leached out in that case. So it says here that water is saturated with a solute at a concentration of 2.5 kilogram per cubic meter. So our C sub S then, the concentration at saturation is 2.5 kilogram per cubic meter. Let me check. Okay, so I will read again the problem. That way you can check and follow through the information that I have placed on our solution. In a pilot scale test using a vessel 1 cubic meter in volume, a solute was leached from an inert solid and the water was 75% saturated in 100 seconds. If in full-scale unit, 500 kilogram of the inert solid containing as before 28% by mass of the water-soluble component and is agitated with 100 cubic meter of water, how long will it take for the solute to dissolve, assuming conditions are equivalent to those in the pilot scale vessel? Water is saturated with the solute at a constant concentration of, rather with the solute at a concentration of 2.5 kilogram per cubic meter. So if there are no questions as to how we have identified the given in the problem and have written it here, we will now go to our solution. I can find my, okay. Okay, for the pilot scale vessel, so in short, we have the pilot scale vessel at 10 seconds, we have the saturation concentration to be equal to. So there was a mention that the water is concentrated already at 2.5 kilogram per cubic meter here in the given. Water is already concentrated at a concentration of 2.5 kilogram per cubic meter. But in the first part, it says that at 100 seconds, is it 100 seconds or 10 seconds? Let me check again with the problem. 100 seconds, so I said 10 seconds. At 100 seconds, 75% saturation was achieved. So in the pilot testing, if I write here at t equal to 100 seconds, we have C sub S being equal to 2.5 kilogram per cubic meter, and we only achieve 75% saturation at this particular time. So our C sub S in the pilot scale vessel is only around 1.875 kilogram per cubic meter, because it was mentioned that in the pilot scale vessel, 75% of the saturation condition was achieved at this time of 100 seconds. Now, at that particular value, we can get then the constants that are not stated in the problem. If you recall, in the PowerPoint slide that was shown to you, there are a lot of constants that will appear in the formula that we're about to use. So the case of the K, the distribution coefficient, the case of the surface area, In the case of the B, these are not available constants. So based on what we have here, we can determine those particular set of constants as a whole, not individually. So if we will consider the formula again, so the formula that we have is C equal to C sub S 1 minus E raised to negative K prime A T over BV. So this is our formula. This is, by the way, class, the saturation concentration. And this one is just the concentration that was achieved at 100 seconds. So this should not be labeled as C sub S, but rather only the C after 100 seconds. Because this one, the 2.5 kilogram per cubic meter is already the constant concentration at saturation. But in this case, for the pilot scale vessel, we only reach 75% of the saturation value. So it should not be C sub S, but rather only the C, because our C sub S is a constant. So if we use this value now in this particular formula, you will have 1.875 being equal to 2.5, and you will have 1 minus E. Then we have negative K prime, which we do not know, the diffusion coefficient. The A, we do not know as well. There was no mention about it. The area of the solid liquid interface. We don't also have the B. So the B, the effective thickness of the liquid film that is surrounding the particles. Now we have the time though. So the time is given to be 100. And the volume of the solution, which is, will be assuming the volume as well of the vessel, is 1 in this case. So we will be getting the value of the set constants which are not available. So the value of the K prime A over B is equal to, you have 0.1386. So you transfer the 2.5 here on the left side, subtract 1 from that, and the rest would be making the left side and the right side of the equation multiplied by -1. That way we can process the exponential function here by making ln on both sides. Then divide by 100. I think this would be the answer that you will be getting. Okay. This is the constant that you will be needing, the same constant since all parameters are the same in the full scale operation. You will have K prime A and B still being equal to 0.1386. So for the full scale vessel, the same formula, the C over C sub S. So I will now place here the constant 1386, and we have the time, and we have the V. Okay, because this one has a different volume, and of course we're trying to find the time. Now your C, your concentration here, the achieved concentration at the time which wherein we want to know how long would that be, would be 75% of the solid, or the other 75% or of the 28% A that is present in your solid. So remember, your solid is 500 and it contains only 28% solute. and that is dissolved in 100 cubic meter of water. So we have, in this case, a value for the concentration which is 1.4 kilogram per cubic meter. So 500 solid, mass of the solid, the entire solid, which has only 28% A, dissolved in 100 cubic meter of water. Now, just like in the pilot scale, your saturation concentration, or the concentration at saturation, is 2.5 kilograms per cubic meter. So if you will substitute this value together with the volume, okay, the volume in the full scale vessel is 100 cubic meter, same as the volume of water that is being used, which we assume to be the same with that in the pilot scale. Whatever is the volume of the vessel, the same amount of volume that will be assumed for that of the solution. So this is the V that we will substitute here. So if we will substitute from to this equation, you will have 1.4 being equal to 2.5, and then you have 1 minus e raised to negative 0.1386. You have the time, which is the one we're looking for, and the volume of the vessel, which is 100 cubic meter. So you will have here a time in seconds, because our time in achieving this constant 0.1386 is in seconds. So the time that we'll be getting here also in the full scale vessel is in seconds. It's 592.34 seconds, more or less equivalent to 9.87 minutes. So this is the time it would take us to extract all, in this case, not just 75%, but all of the solute that is present in our solid. It has to be understood that in here, in the pilot scale vessel, at 100 seconds, only 75% of the saturation concentration was reached. It was stated that way we can get this particular set of constant, the group of constants K prime A over B. But in the second part, wherein we are to determine the time it would take for, this time it would be all the solute. Because in here, we multiply the 500 total mass of the solid, that's the inert and the solute, by the 28% present solute in the solid matrix. So we multiply it by 0.28 and divide it by 100. So in here, it's not 75% of the saturation concentration was reached, but rather 100% in this case. We assume that we took out all the 28% of A in our solid. Okay, but nonetheless, our saturation concentration is still fixed at 2.5 kilograms per cubic meter. Okay, any question here before I go back to the slide? Okay, if there's none, we'll go back to our slide. Okay. Now we are now on this particular material balance equations that will be used for leaching operation. So for total material balance, we only account for A and C. I think this was presented already last meeting. So you will account for A and C present in the feed and C present in the solvent, because most of the time it doesn't have the solute. Then that should be equated to the A and C present in the underflow plus A and C present in the overflow. So the underflow is equivalent to the raffinate in extraction. The overflow is equivalent to the extract in extraction. And M is still referred to as the bulk phase. Now, when we make a component balance or the solute component balance, we just multiply the streams that we have here by their corresponding concentrations. So for the L's, we multiply by the Y's, and for the V's, we multiply by the X, and for the M, we multiply by X also. Now, how we have another balance here, balancing equation for leaching, and that's the B balance. Whatever inert solid is present in the feed, so you have NOLO is the inert solid present in the feed. That should be the same inert solid present in your underflow or in your slurry of solid and liquid solution. So N1 and L1, and that should be the same solid present in the bulk solution M. So you have N, M. So this is another equation. So what's unique about leaching is we still have another equation to use other than the total material balance. And most of the time, it is suggested that you make a solute balance. Okay? So now let's have this very simple problem found in Jean Couplis using single-stage leaching with constant underflow concept. Constant underflow meaning, so as a review again, the amount of solution that is retained by your solid in the slurry is constant. It does not depend on the concentration of that same solution. So it's a constant. Now in this problem, you are given a single stage leaching of soybean oil from flaked soybeans with hexane. Now, hexane was the solvent and oil from the soybean is the A, the solute. 100 kilogram of soybeans containing 20 weight percent oil is leached with 100 kilograms of fresh hexane solvent. The value of N for the slurry underflow is essentially constant at 1.5 kilogram insoluble solid per kilogram solution retained. Now calculate the amounts and compositions of the overflow V sub 1 and the underflow slurry L sub 1. Okay, excuse me class ha. Okay, it's stopped. Okay, that's already multi-stage show. Let's go to our, let me again just get a picture. Okay. Okay, number 2. So we will use the box representation for the leaching equipment. Single stage leaching that is. So you have this. You have the LO, you have the L1, you have the V2 here, and you have the V1. You have 100 kilograms of soybeans containing 20 weight percent oil. So in your 100 kilograms, if 20% is oil, then you have 20 kilograms A, and the rest would be your B. Okay, so in the statement, it says that you have 100 kilograms of soybeans containing 20 weight percent oil. It's going to be leached with 100 kilograms of fresh solvent. So this one, 100 kilograms C. Okay, it's all C. Now you have here the value of N, which is a constant at 1.5 kilogram B per kilogram of solution. So when we speak of solution class, that's kilogram A plus kilogram C. So the solution that we're referring to is only the mass of A and that of C. Now that's it. So this is the only given in the problem. We are required for the V1 and the L1. So the amount of the underflow slurry and the overflow B sub 1. So for our solution, I think in unit ops, it's really forthcoming that you always write the overall material balance as a start. If it will not give you anything, then just set it as one equation. So we do just that. We do the overall material balance. You have LO plus V2 being equal to L1 plus V1. And this is equal to the bulk phase M. Now remember the LO, the V2, the L1, and the V1 here is just your A and C. For the LO, the feed, you will only have the A. So then that would be your 20. Let me see. So it's only the 20. As for V sub 2, you only have C. So that's the entire thing, which is 100. So you place here 100. You don't know L1 and V1, and of course the M, which is equal to 120. So your L1 plus V1 is equal to 120, or we can have V1 being equal to 120 minus L1. And just like what I said, most of the time you don't solve anything out of the material balance. So that's your one equation. You can do solute balance or A component balance. So you will have, you have LO YAO plus V2 XA2 equal to L1 YA1 plus V1 XA1. And this is equal to MXAM. If you notice with this one, you have LO is equal to 20. Your YAO is 1.0, as we have discussed a while ago, because your feed is all A and what you have in the denominator is only A. Your V2 does not have any A because it's all solvent. So this automatically will be equal to 0. Now, here you will have all of this unknown. 4, L1 YA1 plus V1 XA1, and you have your 120 XAM here. Okay. In here, you can get the XAM, but you use this using the graphical approach. But if you want a pure analytical approach to this problem, this would not really be useful if you equate the 20 to 120 XAM, because there's no other formula that you can use the XAM except with the A balance. So we can try the other formula that is suggested. We just discussed it a while ago, and that's the B balance. And we know that NO-LO should be equal to N1-L1. It was mentioned that, or it was mentioned, it was shown rather in the previous slide, that you have this as your solid, inert solid balance equation. So we will get now the NO in the feed. So I will just write it here, use a different ink so that everything will be just in one page. So you will have NO is the concentration of the solid in the feed. So your solid in the feed, is 80. And your A plus C in the feed is just a 20 because you don't have any C. So in this case, you will have an 80 over a 20, which is a 4. Okay? Your LO, we know our LO is equal to 20. So automatically, this one, the 20 and the 4 is actually the 80, which is your solid. Okay? Now, what about N1? Because L1, L1 we can get out of this particular equation. It was mentioned in the problem that your N is a constant at 1.5 kilogram B per kilogram solution for your underflow slurry, the mixture of your solution and your solid. So we can use that here for N1. So you have 1.5 and you have L1. Here, you will be able to get the L1 right away. that should be giving you 53.33. That's the L1. And that same L1 that you will place in here to get your V1. So if you substitute L1 to equation 1, you right away get the V1. And that's your 66.67 kilograms. A and C in your overflow because V1 is your overflow. So in terms of the answers class to the required information, you have these two, the L1 and the V1. Okay, so this is your answer for this particular problem. Now, since this is a sample problem in Janku Place, I will leave to you the that would be your ungraded assignment to read the graphical approach. There's a graphical approach to this problem. You can read that. That way, you will more or less have a second option should analytical approach be something that you cannot right away make use of for certain in some occasions wherein you're given a problem, something like this. Okay, this one can be solved also using graphical technique, but you won't rely on that unless that's the last recourse that we have. Now, any question? Okay, so we'll go back. Okay, so this is the problem that we have. This is the second problem that we have. And this is multi-stage leaching. Okay. Most of the time, this is in the case of a series of thickeners, one situated adjacent, or they are actually adjacent to one another. So you still have the LO, the BO, the NO, and the YO here for the feed. Now this time we have the nth thickener as capital letter N. The small letter n is referring to any n thickener. And we have Ln, B, Yn, and Nn, just like in any separation processes. The only thing that differed here is the X and the Y, which was interchanged. So everything also was defined in here. So V is the mass of the overflow solution, or in the case in this part here, this is your solvent. Now your solvent that carries already your solute is your overflow solution. So that's your V. L is the mass of the liquid in the slurry. So take note, mass of the liquid only. It does not take into account the B. The B is the mass of the dry solute-free solid. And again, the concentrations Y and X. So the next problem that we have, most of the problems in leaching are, shall we say in our language, mano-mano when we solve it, because if you don't want really to use the graphical approach, you have to do material balance in stage-wise fashion. Okay, like from first stage to second stage to third stage and so on and so forth. But the principle that you'll be using is the same as if you're dealing with separate stages. It's just that you need to account the streams that enter and leave a particular stage. So you have here A and C balance still applying A and C balance to our multi-stage leaching process, and then the A component balance in the same way, in the same manner. Okay, now the setup is always something like this. We have the fresh solvent here, and most of the time that fresh solvent is mixed with the concentration, with the solution of A and C. Okay, the solution of A and C coming from each of the thickeners numbered in this fashion here. So this is your thickener 1, this is your thickener 2, and this is your thickener 3. If you recall, we said we numbered the thickeners or the stages where the solid is being introduced. So since the solid is being introduced in this first part here in this equipment, so this is our thickener 1, this is our thickener 2, and this is our thickener 3. Our wash solid or our spent solid, the solid that contains very little if none of A, is the solid that leaves the last thickener. Now, since as I've said, the manner of doing material balance for leaching is stage by stage, we will discuss the solution of this three-stage thickening apparatus or system next week when we resume class already next week. That's on a Monday. Okay? So far, any question for now? None? Okay. So I will dismiss the class now. We'll continue with the last part of this. Then have the intro to adsorption on Monday next week. Okay? Enjoy your Holy Week. Bye now bye now class. Thank you for the heart, Earl.